This lecture will be the Chapter 9 lecture on stoichiometry in first-year chemistry class. We first covered the definition of what stoichiometry means. It refers to calculations of chemical quantities from a balanced chemical equation. So basically we're going to be doing conversion problems where we have a balanced chemical equation and we're going to determine the amount of starting materials or products that you have or you can make if you know the balanced chemical equation. So here's an everyday equation. When I was in high school, we had a basketball team that was composed of 2 guards, 2 forwards, and 1 center, and that made up our team. And so I'm going to abbreviate the guards as 2G, and the forwards as 2F, and the center is just the letter C. And then it makes a basketball team. So the formula for a basketball team is going to be G2F2C. So what we're going to do is look at this everyday equation, and we're going to determine the answer to these questions. It says, how many guards does it take to make 7 teams? Well, if you look at the ratio of guards to teams, it takes 2 guards to make 1 team. So if you want to make 7 teams, you're going to have 14 guards. And now we ask, how many forwards are there in 8 teams? We do the same thing. If you look at the ratio of forwards to teams, again, we have this ratio of 2 to 1. So for every 2 forwards that you have, you would only make 1 team. So if we're going to try to make 8 teams, we're going to need 16 forwards. In question number 3, we have 8 centers, 17 forwards, and 14 guards, and we want to know what's the most number of teams that you can make. Well, let's go through them one by one. If you have 8 centers, you can make up to 8 teams. If you have 17 forwards, you can make 8 teams, but then there would be 1 forward left over. And if you have 14 guards, you can only make 7 teams. So the maximum number of teams that we can make is only 7. And the question that's asked next is, what do you run out of first? And the answer was guards. So these are a lead-in to what stoichiometry is about. We have a balanced equation and we're determining how many reactants or products we're going to form, or how many reactants or products we need. And we also are going to look at what item is going to run out of first, and that's the concept of limiting reactants or limiting reagents, which is in this chapter as well. So on the next slide, we're going to look at a real chemical equation. We have the formation of ammonia from the elements nitrogen and hydrogen. So the first thing we need to do is balance the equation, and once you have the balanced chemical equation, you can look at the kinds of information that you can get. So we have this ratio of 1 to 3 to 2. Well, that means we have 1 mole of nitrogen and 3 moles of hydrogen, and that produces 2 moles of ammonia. We also can look at the 1 to 3 to 2 ratio as being the number of molecules that react, and it can also be the number of liters that react as long as these substances are gases, which they are. But for a number of grams, it's not going to be 1 to 3 to 2. The ratio of grams comes from the periodic table. It comes from the molecular weights of these substances. So if you have 1 mole of nitrogen, that would be 28 grams. If you had 3 moles of hydrogen, that would have a weight of 6 grams, and the mass for the ammonia, if you had 2 moles of that, it would be 34 grams. Now you don't really need to look at the periodic table for the last answer, because if you had 28 grams of nitrogen, if it's going to react with 6 grams of hydrogen, 28 plus 6 better equal 34, or something's gone wrong. So we have conservation of mass occurring in that last line. Now the first type of conversion factor that we're going to look at is the very simple mole-mole conversion factor. Now the mole conversion factor, the ratio, comes from the coefficients of the balanced chemical equation. And I get tired of saying balanced chemical equation in class, so I just abbreviate it BCE. So if I use the term BCE, that means the balanced chemical equation coefficients. So we're going to set up a conversion factor that changes from moles of one substance to moles of another substance. So in each practice problem, we only have 1 given. We're going to write that down with the times line. In the first example, we have 7 moles of nitrogen. That's our given. Our times line will have the units of moles on bottom, and the number of moles of nitrogen that we're going to use is 1, and that comes from the coefficients in the balanced chemical equation. And if we want to figure out how many moles of ammonia can be made, we need to use moles of ammonia as the top part of our ratio. And the number for ammonia, again, comes from the coefficients of the BCE, and that's the number 2 in front of the ammonia molecule. So if you have 7 moles of ammonia, you can make twice as many moles of ammonia, and so that answer is going to be 14. Now you could do that problem in your head. You see the ratio is 1 to 2, so for every 1 nitrogen you can make 2 ammonias, so the math isn't really that difficult to do. But later on we will have more difficult ratios, so it's best to know the process of setting setting up a one-step conversion factor. In question number 2, we go through the same steps. We need to know how many moles of hydrogen are required to completely react with 8 moles of nitrogen to produce the ammonia. So we have 8 moles of nitrogen as are given. We'll still have the same times line. We'll still have 1 mole of nitrogen on bottom from the BCE, and then we will need the number for hydrogen on top, and this time it's going to be 3 hydrogens. So for every 1 mole of nitrogen, you need 3 moles of hydrogen. You multiply it out, your units cancel, and you get 24 moles of hydrogen are needed to completely use up all the nitrogen. Now I need to go back to the first question. It says that we had the unknown being the moles of ammonia, and we had 7 moles of nitrogen, and I forgot to mention this little fact. It says that we have an excess of hydrogen. That means we don't have to worry about running out of hydrogen, so you can kind of ignore the hydrogen molecule in that first example. In example number 2, we're using up all of the nitrogen, and so we're going to completely use up all the 8 moles of nitrogen, so there really isn't any extra nitrogen hanging around. We won't have extra hydrogen, so it would take exactly 24 moles of the hydrogen to use up the 8 moles of nitrogen. In the last example, we have this question. It says how many moles of hydrogen are needed to react with an excess of nitrogen, and so there's that term again, excess of nitrogen, so we don't need to worry about running out of nitrogen. And we're going to try to make 10 moles of ammonia. So 10 moles of ammonia is our given. That's our starting point. We're going to cancel out that unit moles of ammonia on bottom with the number 2. It comes from the balanced chemical equation coefficient. And then for hydrogen, that's what our unknown is. The moles of hydrogen go on top, and the coefficient is 3 from the BCE. The units cancel out, and you do the algebra, and it's very easy to do. You get 15 moles. So those are one-step mole-mole conversion factors. Now it turns out in this chapter all of our conversion factors will have to have the mole-mole ratio. So we're going to come back to this mole-mole step very often in this chapter. On the next slide, we're going to do other conversion problems that involve 3 steps. So the first type is called mass-mass. We're going to start with a mass unit of one substance, and we're going to convert that to the mass of another substance. So for example, let's say you're cooking a cake. You want to know, let's say, how many grams of eggs would turn into a certain grams of cake. So you would convert grams of eggs to grams of cake. That's just a common everyday example, using grams to grams conversion factor. Well, in our example, in our practice problem, it says how many grams of ammonia can be made from reacting 39 grams of nitrogen with an excess of hydrogen. So we're going to convert the grams of nitrogen, a reactant, to grams of ammonia, a product. So we start out with the given, and that's step 1, which is shown up above. It says write down the given, and you're going to convert from grams to moles. You always go to moles first. I can't stress that enough. When you're doing one of these 3-step problems, you have to go to moles first. So we know the unit of grams has to be on bottom, and anytime you have grams, you have to look up the molar mass of the substance. In this case, it's the nitrogen molecule, which weighs 28 grams, and that is again 1 mole. So the number 1 mole will go on top every time for your first step. The units cancel out, and then we have to do our next step. Now we're going to change from the substance of nitrogen to the substance of ammonia, and this is our mole-mole ratio, which comes from the coefficients from the BCE. It's 1 for nitrogen, and it's 2 for ammonia. The units cancel out, and we do the last step. Now that we have moles of ammonia, it's very easy to convert to grams of ammonia, because this is, again, one simple step. We have 1 mole of ammonia on bottom, and we just need the molar mass of ammonia, and we know that's 17 grams from the periodic table. And the units cancel out, and you get your final answer. 47.4 grams of ammonia. So if you start with 39 grams of nitrogen, that would produce 47.4 grams of ammonia. The 3-step conversion problems are very, very similar to one another. The first step is 1 mole, the middle step is the mole-mole ratio from the BCE, and the last step has 1 mole. So the first step has 1 mole conversion, the middle step is mole-mole, and the last step is 1 mole. So they're very systematic, and you'll find myself repeating these facts over and over when we do the next practice problem on the next slide. This time we're going to have volume mass problems. We're going to start with the volume unit, which is liters. We're going to convert to moles. Then we're going to do our mole-mole step, and then we'll end up with the mass unit, which is grams. So let's look at the practice problem. It says how many grams of ammonia can be made from reacting 20 liters of hydrogen with an excess of nitrogen. So we start with the 20 liters of hydrogen as our given, and in order to convert this to moles, which is always our first step, we need to use the factor of 22.4 liters is equal to 1 mole. The middle step is the mole-mole ratio. We're changing hydrogen into ammonia. The number for hydrogen is 3 from the balanced chemical equation, and the number for ammonia is 2, so that's our mole ratio. And then we change moles of ammonia to grams of ammonia just like we did before, so our conversion factor is the same, 1 on the bottom and 17 grams on top. And that's the 3 steps we need to change liters into grams, and you get 10.1. The next problem is very similar to the previous one. Instead of volume mass, we're going to do mass volume. So we're going to start with the units of grams, convert it to moles, do the mole ratio step, and then convert to the volume unit, which is liters. So in the practice problem it asks, how many liters of ammonia can be made from reacting 36 grams of nitrogen with an excess of hydrogen? So 36 grams is the given amount of nitrogen. We convert it to moles by using the molar mass on bottom. We already know that's 28. We used it before. It's always going to be 1 mole on top. Then we do our mole ratio step. We're changing nitrogen into ammonia. The number for nitrogen is going to be 1 mole. That comes from the coefficient in front of the nitrogen molecule in the BCE. The number for ammonia is 2. And the last step, we're going from moles of ammonia to liters. We always use 1 mole for the last step, and the number of liters is always 22.4. So just to reiterate, the first step always has 1 mole, the last step always has 1 mole, that middle step, the numbers change depending on what the coefficients are from the balanced chemical equation. You do the algebra, you end up getting 57.6 liters. Finally, a volume-volume conversion problem is actually treated exactly like a mole-mole conversion problem, and the reason we can do this as a 1-step problem instead of a 3-step problem is because the volume conversion factor for all gases is 22.4 liters. So the volume ratio is 1 to 3 to 2, and the mole ratio is 1 to 3 to 2. So we're going to convert liters of ammonia, we're going to convert liters of hydrogen 2 liters of ammonia. So we start with the given 125 liters of hydrogen, we put a little times line, and then in 1 step we can convert liters to liters. There are 3 liters of hydrogen, that's from the balanced equation, for every 2 liters of ammonia. So 3 goes on bottom, 2 goes on top, and again those are the coefficients from the equation, and you get an answer of 83.3 liters of ammonia. Now, here's the long way to get the same answer. If somebody didn't recognize that volume-volume was a 1-step problem, you could do it in 3 steps. You would set up your little times line, convert liters to moles, it's 22.4 liters on bottom, 1 mole on top. Your middle ratio is still going to be 2 on the top and 3 on the bottom. And then your last ratio, you're going to go from moles to liters. So again, you'll use 1 mole on bottom all the time for the 3rd step, and you're going to be using 22.4 liters on top again. Now if you notice, you'll have 22.4 liters on bottom, 22.4 liters on top, and they cancel out. So you're basically left with just the mole-mole ratio, which is the same thing as the liter-liter ratio, and so you get the same answer. The next topic of discussion is the limiting reagent, or the limiting reactant. The textbook that we use uses the term limiting reagent, but I kind of prefer limiting reactant because we talk about reactants and products. So either way, it means the same thing. It's basically the substance that you're going to run out of first in a chemical reaction. Now, the reactant that is in abundance is called the excess reagent. So here's a common example. If you had 8 car bodies and 48 tires, you could make 8 complete cars, but you would have 16 tires extra. So the thing that's limiting the amount of cars that you can make is the car bodies. So the car bodies is your limiting reactant, and the car tires are in excess. Now, a real example would be the reaction shown between the hydrogen molecules and the oxygen molecules to form water. We have a 10 to 7 ratio of molecules. Now, to make water, you need a 2 to 1 ratio. So for every 10 hydrogens, you only really need 5 oxygen molecules, and that's why there's 2 oxygen molecules that are left over. And then another way to look at it is that if you had 7 oxygens, it would have taken 14 hydrogens to use up the 7 oxygen molecules. So we're running out of the hydrogen, and so hydrogen would be classified as the limiting reactant, and the oxygen would be the one that's in excess. So we're going to look at how to do this calculation if you're given decimal numbers or a weird number that you couldn't just do in your head, as these examples we could do in our head. So we're going to look at the way to calculate the limiting reactant or the limiting reagent. So what we're going to do is we're going to do a mole-mole conversion for one of the substances, and we're going to calculate how much of the other substance we need to use it all up. Then we have a comparison that we need to do. We're going to look at if we're given enough of the substance, and then you can determine if you have enough, you're not going to run out of it, and if you weren't given enough, that's going to be your limiting reagent. So we have a choice. It says we have 2.7 moles of nitrogen given and we have 6.3 moles of hydrogen given. It doesn't really matter which one we're going to choose as the official given. The other number will just be used as a comparison later on. So we're going to figure out which you run out of first, the nitrogen or the hydrogen. So I'm just going to choose the 2.7 moles of nitrogen as the given just because it starts, it's the first number I run into in the word problem. So we're going to figure out how many moles of hydrogen we need to use up 2.7 moles of nitrogen. So we set up our little times line. This is going to be a one-step mole-mole conversion. We put the number for nitrogen on bottom from the BCE, the number for hydrogen on top from the BCE, and the units cancel out. And we have now calculated that it takes 8.1 moles of hydrogen to use up all of the nitrogen molecules. Now we have to ask ourselves, were we given enough hydrogen? Well, if you look back at the question, it says that we were only given 6.3 moles of hydrogen. So were we given enough? Clearly no, we're not. We needed 8.1, they gave us 6.3, so we're going to run out of it. In the next example, it's basically the same way. We have 3.9 moles of nitrogen. It's trying to react with 12.1 moles of hydrogen. Somebody's going to run out first, so we'll figure out how much hydrogen we need to use up all 3.9 moles of nitrogen. So 3.9 moles of nitrogen I'm going to choose as the given. We put a little times line. The ratio is going to be identical as before. 1 on bottom, 3 on top. The units cancel out, and we can see that it takes 11.7 moles to use up the nitrogen. Now we have to ask ourselves, were we given enough hydrogen at the beginning of the experiment? Well, we were given 12.1 moles of hydrogen. We only needed 11.7 moles, so yes, we do have enough. So if you have enough hydrogen, you're going to clearly run out of the nitrogen. So nitrogen becomes the limiting reagent or the limiting reactant. Now, if you look at how much extra hydrogen we have, it's clear to see that we have 12.1 given, 11.7 moles is how much we needed, so we're going to have 0.4 moles left over. We're going to calculate the excess reagent on the next page. So how many moles of excess reagent do we have? So what we're going to do is we're going to do the conversion problems again, but we're going to start with the limiting reagent as the given. So in the first example, the limiting reagent was the hydrogen. So we have to use 6.3 moles of hydrogen as the given, and we're going to figure out how much nitrogen we really needed. We have some extra nitrogen, so we're going to figure out how much that is. So when you do the algebra, our ratio is going to be 3 on bottom, 1 on top. That's from the BCE. And you only really needed 2.1 moles of nitrogen for the reaction. And we were given 2.7 moles of nitrogen, so we have 0.6 left over, and that's from a simple subtraction. And I'll let this finish the animation. There you go. Now in the second example, we got lucky. We started with the limiting reagent. And so we already know that we were given 12.1 moles and we only needed 11.7 moles, so we have the hydrogen left over. So we already started with the nitrogen, which was the given in the second practice problem. So if you want to find the limiting reagent, you have to do a one-step mole-mole problem, and then you have to compare how much you calculated, which is the needed amount of moles, to how much was given in the original question. The last slide deals with percent yield calculations. Percent yield is a ratio that tells us how efficient a chemical reaction is. So when you run a reaction, you might have some splattering, you might do a lab procedure incorrectly, or you might follow lab techniques and lose some of your product during the experiment, or maybe your experiment takes multiple steps and you lose some product. And so the percentage of product that you actually produce compared to what you're supposed to produce, that gives us a percent yield. So for example, when you're baking a cake, you'll notice that when you're finished mixing the ingredients, some of your batter might not make it all into the cake pan. Some might be stuck on the spoon or the mixing bowls or your batter mixers or whatever, and so you're going to be losing some of your product there, and so that would be an example of a common percent yield, that you don't quite get 100% of all your cake mix into the cake pan. So anyway, here's some definitions. The actual yield is the amount you experimentally get when you actually run the reaction in a lab. The theoretical yield, or the ideal yield, what you're supposed to get, is a calculated stoichiometry problem. It's the amount you're ideally supposed to get if everything goes perfectly and you don't lose any of your product. So we're going to look at a couple examples of percent yield calculations. So here's the first one. A student reacts 40 grams of hydrogen with an excess of oxygen, so hydrogen is going to be your limiting reagent, and it produces 300 grams of water. Now, you're not supposed to produce 300 grams of water. You're actually supposed to produce more than 300 grams, but we're going to find the percent yield for the reaction. So we're going to do a conversion problem starting with the 40 grams of hydrogen. You always start with the reactant. So we have 40 grams of hydrogen, and we're going to figure out how much water we were supposed to actually make. And we're going to convert grams to moles, the first step of any three-step problem. We find 2.0 grams from the molar mass on the periodic table, 1 mole always for the first step, and we're going to change moles of hydrogen to moles of water, and this is a 2-to-2 mole ratio, and that comes from the BCE. And the last step, we're going to convert moles of water to grams of water. We use 1 mole for the last step, and the molar mass for water on the periodic table is 18. When you do this calculation, we were supposed to make 360 grams of water. Now we actually only made 300 grams of water, so what percent is that? Well, 300 out of 360 happens to be 83.3%, so that's our percent yield. On the next page, we do a very similar question, but just something a little different happens. We have 2 grams of hydrogen, and it completely reacted with 16 grams of oxygen, so there's no limiting reagent. They all get used up. Or maybe you could say they're both limiting reagents. So anyway, nothing's in excess. So we have more information in this question, so we don't have to necessarily do a conversion problem to figure out how much water you are supposed to make. 2 grams of hydrogen reacting completely with 16 grams of oxygen should have ideally made exactly 18 grams of water. Now, it says in the question that we only produced 17.5 grams of water, so the percent yield is just 17.5 out of 18. Multiply by 100 to convert it to a percent, and it's 97.2% efficient, or that's our percent yield. So that's basically the notes from chapter 9. They come into 4 categories. The problems that we do are either mole-mole conversions, the 3-step conversions converting from grams to grams or liters to grams, or you could even do molecules to liters. So it's a 3-step conversion problem. Then there's limiting reactant problems, and there's also percent yield questions. And that's basically a summary of what we do.